Okay, hi. Thank you for giving me the chance to speak. My name is Dinushi. I'm a Ben student. I'm going to be talking about q-Schur algebras in type B. So before we kind of get into the meat of what I'm going to talk about, just some notation and conventions. The Hecke algebra of type A kind of has the usual braid relations that everyone knows about, but the convention that I'm using for the quadratic relation is that the roots are q and -1. So then moving up to the type B Hecke algebra, we're going to add an extra generator T0 with quadratic relation with roots capital Q and -1 and one extra braid relation. So we are working with the unequal parameters case. So we're going to see an x lambda floating around. This is a symmetrizing element for some parabolic subgroup of Sn. So a thing to note for this is that this kind of sum of Hecke algebra elements only contains type A guys, so there's no T0 floating around in this. However, when we go to type B, we'll have a U sub lambda for lambda a bipartition, which is kind of built out of these Juices-Murphy elements. So I guess everyone here is familiar with the classical Schur algebra that comes out of classical Schur-Weil duality. So we have our first kind of generalization away from that. In 1989, Dipper and James constructed this quasi-hereditary cover of the type A Hecke algebra by taking the endomorphisms of this collection of modules. This algebra is isomorphic to kind of what you get if you take the group algebra of Sn and kind of add a quantum deformation and then onto this nth tensor space, and then kind of look at the Hecke invariant endomorphisms of that. So obviously we want to generalize this into type B. And so the first generalization that we have, properties of this. So this algebra is cellular. It's a quasi-hereditary cover of the Hecke algebras of type A, and it is categorified by singular circle bimodules. So it's very nice. On the one hand, we have the first generalization done by Dipper, James, and Mathas in 1998, which was to construct quasi-hereditary covers of cyclotomic Hecke algebras. So you kind of see that the modules that are constructed kind of look kind of similar. There's a new type B factor for the U lambda, and we take the endomorphisms. On the other hand, looking at this side of these two kind of ways to realize this algebra, we might say, okay, well, we have a type A Hecke action on the nth tensor space. Type B is just one new generator. What happens if we kind of give this new generator an action in the most natural way, and then take endomorphisms of that? So that is the approach that Lai, Nakano, and Xiang took in 2020, building on the equal parameters case done by Bao, Xiao, Li, and Wang. So for the next 6 minutes or so, I'm going to be referring to the one that everyone kind of knows as the cyclotomic q-Schur algebra, as the Dipper, James, Mathas Schur algebra, and the one built as this endomorphism algebra as the LNX Schur algebra. So what happens in type B, unlike in type A, is that we don't have the same algebra if we take these two approaches to building it. So first off, we know a lot of properties. These are all from the original Dipper, James, Mathas paper introducing this construction, which is, first of all, the simples correspond to the bipartitions. So that's a nice combinatorial parametrization. Furthermore, it's a cellular algebra with a cellular basis indexed by pairs of bitableau on 2 alphabets. So cellularity also gives us a lot of structure with these cell modules, finding the simples as quotients of the cell modules, the inner product, etc. And by construction, it's quasi-hereditary for all parameter values of Q. So on the other hand, we look at the LNX Schur algebra and we don't have answers. So One thing we do get, though, is this nice bonus fact that this is the algebra that is categorified by singular circle bimodules in type B. So maybe that's reason enough to care about it. Yeah, so our first result, kind of the big picture of what we're doing, is taking the ln(x)-Schur algebra and sticking it inside the larger cyclotomic q-Schur algebra to kind of use everything we know about this Difford-James-Mathas construction to learn stuff about the ln(x)-Schur algebra. So we know that there is an idempotent E that lives inside the cyclotomic q-Schur algebra that you can use to write the smaller algebra as a corner algebra of the larger one. In particular, this idempotent is invariant under the involution that you get with the cellular structure. So there is a result by Dinushi that says that this just means that we're going to get all the cell structure inherited down into the smaller algebra. So this kind of tells us, yeah, so right away we have it cellular with the structure inherited from the larger algebra. And we can kind of use that information to answer the other two remaining questions, or attempt to so far. So the first thing is that we're going to get simples just by cutting down the original simples by the idempotent, as long as we don't lose them. So we might lose them, but if we don't, we get our simples. And oh, I'm very fast. This algebra is going to be quasi-hereditary if and only if we're not losing any simples. So what's nice about knowing that the algebra is cellular is that this now becomes a matter of computing the bilinear form on each of these cells. So we're going to lose a simple if and only if the cut down cell module is going to have a 0 bilinear form. So that's kind of what we would try to do. And yeah, so that's useful because then if you can write each of these bilinear forms as kind of polynomials in the parameter values, then your roots are basically just where you're going to lose simples and where you're going to lose quasi-hereditary. Yeah, so we already know that it's not going to be quasi-hereditary when q is minus q to the k for k between 0 and n. That was just kind of a combinatorial argument looking at one of the cells corresponding to like the column and then empty. And we hope to prove that the algebra is not quasi-hereditary if and only if q is a negative power k, sorry, capital Q is a negative power of small q for k between 4 minus n over 2 and n. So this is a modification of the conjecture that Nakano and Xiang gave in their paper. They slightly overestimated the bad parameter values. So we have a counterexample to theirs, and then this is the modified, hopefully provable version. Yeah, in the, I guess, context of this workshop, the way that this will hopefully be proved is by looking at induction and restriction functors on the simples of the ln(x) guy. So when you kind of take the crystal graph of the cyclotomic q-Schur, you can cut it down with an idempotent to get information about the simples of the Hecke algebra, and you lose some parts. And hopefully this is kind of like an in-between case. So that's the goal. Thank you.